Hello, and welcome to this video. In this video, we're going to take a look at the theory behind radioactivity. So, we should already be familiar with the fact that we can have certain substances that are radioactive, and we know the paths that they are radioactive through, right? So we can have alpha decay, beta plus decay, even electron capture, gamma decay, all of these kind of things. But what we have to say is, as physicists, we can observe this stuff, but it's not really enough. We need to understand this. We need to be able to actually get a decent idea of what's actually going on, what's causing that to happen, and how can we predict something that's going to happen based on our observations. We need a theory of how radioactivity works. Now, the first thing we have to see is that we have different paths that radioactive substances can go down, right? So some radioactive substances will decay through an alpha, some will decay through a beta, some will just emit gamma rays. Now, we then have to say what exactly is the difference. Why do some go down one path and why do others go down the other? And the reason is because of this stability curve. This stability curve gives us an idea of how we can predict whether a individual isotope or individual element is going to undergo a certain amount of decay. Now, explaining you guys through this black line that you see here is the N equals Z line. Now, what that means is N is the number of neutrons, and Z is the number of protons. So we're saying that this black line would be the line where the number of protons is equal to the number of neutrons. But that is not the stability curve, because obviously that's a straight line. It's this blue line here. This is your stability curve. So any element that lies along this, so if I were to, for example, find something that was like 10 protons, 10 neutrons, that would be this position here, that element is stable. If I were to find something that had like 60 protons and about 80 neutrons, that element is stable. These things aren't going to be radioactive. So anything that lies along this line is found to be not radioactive for the most part. Okay, obviously there are some exceptions to this, but in general terms, if we have something that lies on this stability curve, that is a stable molecule, so it won't change in any way. Now, we then have these dots, and all of these dots are isotopes that we have found, and these have already been labeled on the diagram as the beta minus emitters and the beta plus emitters. Now, let's first go through the beta minus emitters. So let's switch to green to be consistent, and it's anything above the stability curve emits beta minus. Okay, so we'll look at beta minus emitters. So anything that lies above this curve therefore has more neutrons than protons. So these are neutron-rich elements. And this is why they will undergo beta minus decay. We know that beta minus decays when a neutron decays into a proton, releasing this beta minus and an anti-electron neutrino. Now, because they are neutron-rich, their whole goal is to try and decrease the number of neutrons. So a neutron that is contained within this nucleus then decays into a proton, meaning we're basically shifting one down and one across, so like diagonally across a single block, which is then going to take us closer to this stability line. Okay, so this is a radioactive method in order for a neutron-rich element to try and become more stable. If we had the opposite of this, we go underneath this line, we end up with the beta plus emitters. Now, the beta plus emitters have too few neutrons, so they are neutron deficient. Now, I'm also going to describe this as being proton-rich. Right, so we have isotopes of this that have too many protons and not enough neutrons. So what they do is the beta plus mode is the proton decays into a neutron, releases a beta plus and an electron neutrino. Now this then means that whenever you have a beta plus decay, the number of protons decreases, the number of neutrons increases, and hence you're getting closer to this stability curve. And so these two methods are two of the few ways that we can actually get something to be more stable. And now we have this kind of idea of how we can predict whether something is going to be beta minus or beta plus, because if it has too many neutrons, so it lies above this stability curve, it will be a beta minus emitter. If it has too many protons and lies below this curve, it will be a beta plus emitter. Then we have to say, we also know that we can have an alpha emitter, okay? And I'm going to use this gray pen to represent the alpha emitters. So I'll do this over here. Now the alpha emitters, we know that alpha decay is when we release a full helium nucleus from the nucleus of whatever this radioactive isotope is. Now for that to happen, not only are we decreasing the number of protons in that parent nucleus, we're also decreasing the number of neutrons, which means that it can't have just been a proton-rich or a neutron-rich nucleus. It had to have just been a nucleus that's just too big, okay? And what we find is that usually anything that passes this proton number of 80, anything on this side of this line, so it tends to be molecules that are around up here, they tend to be alpha emitters. So if the proton number is greater than 80, they are alpha emitters. But that's not just because they've got too many protons, it's because obviously as this line goes up, we're going to end up with many more neutrons for every proton, okay? And that is why they're alpha emitters. This is when we get to the massive elements or massive isotopes where they're just too big. And the last one that we can look at are the gamma emitters. Yeah, this is the last kind of radiation that we can get. And actually the gamma is just excess radiation that is, or excess energy that is left over when we go through one of these three paths. So after an alpha decay, a beta decay, a beta minus or beta plus, it is very common to get a gamma decay given out. Okay, so gamma usually follows an alpha or beta decay because it is just the excess energy from the nucleus being released. So it's just excess energy released. Now, we have this idea of predicting if we get given an individual isotope, we can then predict what type of radiation is it going to emit, if any. Now, I should mention that these don't always happen individually, right? So we can get things called radioactive series. And in a radioactive series, we end up with multiple different types of radiation being emitted by the same molecule. So multiple radioactive modes. Now what I mean by that is we can have the same substance that is emitting alpha as beta and gamma. So some of these radioactive substances just go all out and emit all the radiation that they can contain. Now the reason for that is because the whole purpose of undergoing these radioactive interactions is to try and get closer to the stability curve. Now what they find is by changing certain numbers, they will find themselves kind of hopping from one side to the other. So if we, for example, if I make a rough sketch of this stability curve, so this is the neutron number, this is the proton number, and it looks something like this. And that's kind of your line of equality where they're both the same. Let's say I had a molecule that was here, okay? And let's say that this line here is when this is 80. So I know it's going to be an alpha emitter. Now on a grid, if I know that I have an alpha emitter here, it's then going to lose 2 protons. So I'm going to go across and let's say this is a grid that looks like this, and I'm in the top corner of this grid, I'm then going to lose 2 protons, so I'm going back 2, and I'm also losing 2 neutrons, so I'm going down 2. Now, this position here might now be on this side of the line. And once it's on this side, so I have 1 alpha decay. Once it's on this side, I now have something that has less than 80 protons, so I'm looking at something that's no longer going to decay by alpha, but will now have too many neutrons, and it will now decay by beta minus. Then, when it decays by beta minus, the number of protons is going to increase by 1, and the number of neutrons decreases by 1, so I go across down like this on this grid. And I now have a new isotope, and that new isotope might now be on the other side, and it will undergo beta plus decay. Now when it undergoes beta plus decay, it is then going to undergo, it then has too many protons, so it loses 1 proton, so it's going to go this way, but it gains 1 neutron, so it's going to go back up to here. And then maybe here I'm then just going to get a constant switch between these. Maybe sometimes I'll get a molecule that's going to perform a few beta minus, and then maybe 1 beta plus, then maybe an alpha, and so on. Right? So radioactive isotopes will emit radiation to get as close to the stability line as they can. Okay, so now we have a kind of prediction, as we can estimate using our knowledge of these observations. If we get given a certain isotope, we can predict what path it's going to take, whether it's going to be a single emission of alpha particles, whether it's just going to be a single beta minus or beta plus, or whether we're going to have a series depending on obviously the position of where it is. So what we can know from the stability curve is what type of radiation are we going to emit. The next thing we need to then do is say, how can we predict when that type of radiation is going to be emitted? And actually, we find that we can't. Okay? This is then a kind of idea that radioactivity is completely random, as far as we're concerned. Okay? Now, this means that it is entirely down to probability. So we can kind of make an estimate of when we think something is going to undergo some radioactive decay, but we can never pinpoint the exact time. For example, if we were doing like classical mechanics, or we were doing some sort of Suvat equations, we could pinpoint the exact moment that a ball passes a point. But we can never actually pinpoint the exact moment with 100% accuracy of when an isotope is going to decay. So that means we have to entirely base all of our predictions off of probability. So we have to model radioactivity by probability. Now this is where it gets a little bit mathsy. So for anyone who's doing A-level maths or A-level further maths, you would be familiar with the idea of modeling by differential equations. Now for anyone who's not familiar with this, I'll go through it very briefly. You don't have to know the complex maths behind it. But basically what I'm going to say is I start with a radioactive source. Now, when I say radioactive source, a radioactive source does not mean a single isotope. It means I have a bunch of atoms or elements, right? So when I have a radioactive source, I'm not looking for just a single molecule that is gonna, or a single element or atom that is gonna emit radiation. It's very difficult to isolate a single atom. I'm gonna have like a bunch of them that are all gonna emit radiation. So a radioactive source is made of a large amount of isotopes. Or actually, let me call them atoms. Yeah, so they could all be the same isotope, so the same ratio of protons to neutrons, but not necessarily the same atom, so you can have a bunch of them. And what that means is, what I want to know is, as these decay, I want to know, how does the number of undecayed nuclei change over time? So what I'm going to say is, I want to know how quickly the number of decayed nuclei, or the number of undecayed nuclei, changes. So I want to know the change in the number of nuclei over time. Now, I can come up with some rough idea of this, and I know, for example, that it will be dependent on the number of particles that I start with, or the number of atoms that I start with, or the number of atoms that are currently in the radioactive source itself. If I start with a huge amount of atoms, I'm going to end up with a very high rate of decay, because surely that means that if I've got loads of them, it's way more probable for them to all decay, and hence I'm going to have it happening quicker. If I have maybe one or two, then my rate of decay is going to be much slower. So I know that this is going to be dependent on n, okay, where n is the number of particles that I have. Now I also know that this is going to be a decrease. So this has to decrease, because I know that if I'm looking for the number of nuclei that haven't decayed yet, as time goes on, more and more of them are going to decay, so I'm going to get less of them that haven't decayed. So I know this is going to be negative, because it's a change. It's going to be a negative change because I'm decreasing. Now, in order to actually finish off this equation, I'm just going to introduce a constant. Okay, now this constant we call the decay constant. So lambda is the decay constant, and we will talk more about the actual idea of what the decay constant represents in a separate video. In this case, we just have to be aware that the decay constant is kind of just introduced as a mathematical way of representing this relationship. So this is this is on your formula sheet, and this is our model of radioactivity based on probability. So this is saying we assume that it does something that looks a bit like this. And what happens when we look at observations from radioactive sources is this exact trend. We see that it is proportional to the number of molecules that are currently in the system, and also some random decay constant, because that decay constant will be different for each radioactive isotope. Now, I mentioned at the introduction of this that this is a differential equation, which means I can solve this differential equation. Now, this next part, for the next minute or so, none of you have to know, but if any of you are doing maths, you might find this useful. So basically, I'm going to say that I could rewrite this and change these deltas for dn by dt is equal to minus lambda n. Now, if I want to solve this as a differential equation, I need to get everything that's dependent on n on one side and everything that's not dependent on n, or anything that's dependent on t, on the other side. So I then rearrange and I end up with dn over n, so everything that's dependent on n, is equal to minus lambda dt, everything that's not dependent on n. Now, when I have it like this, I can integrate both sides, and when I integrate both sides, I end up with log of n is equal to minus lambda t plus some sort of constant. Now, I don't know what this constant is because I haven't got any indication of an initial condition yet, but then I need to rearrange, because I can then say, given this, I can come up with an expression that gives me the number of molecules in this system at any given time. Now, in order to do that, I need to get rid of this log. So I'm going to put everything on the right-hand side in an exponential. So this becomes n is equal to some constant a from here. So where a is e to the power of c multiplied by e to the minus lambda t. Okay. Now I know that this is an exponential decrease, okay, which makes sense because the number of particles in the system is going to decrease, so it might as well be exponential. So if this is an exponential increase, then at time t equals 0, so when t equals 0, A must give me the number of particles initially at the beginning. Because if I put t equals 0 here, this whole e to the minus lambda t becomes 1. So therefore n must be n, right? So therefore this must lead to A is equal to n naught, which is what we're going to call it. And then we have our second equation. N is equal to n naught times e to the minus lambda t, where n naught is the initial number of atoms. Lambda is the decay constant, and t is just the time that as it's going along. And this then tells us that whenever we have any type of radioactive decay, it's always an exponential decay. So radioactive decay is exponential. Now, these two equations are the first two that you're kind of introduced to on the equation sheet for nuclear physics, and they form the basis of the theory of radioactivity. Now, like we say, these are based on probability, and they're entirely based on initial conditions. There's no way that we can then say for every isotope of this molecule will have n amount of molecules at this time, because it's entirely dependent now on what we started with. And if we're trying to count out a number of atoms, that's ridiculously difficult, right? So it means that these have now started our basis, but we can't quantify anything between these. We can't compare the amount of radiation emitted. We can't see what's more radioactive than the other. What we can do is come up with a loose idea of how rapidly is this thing going to decay. Okay, now in the next video we're going to go through activity and half-life, which are how we're going to use these ideas to then go forward and explain how we can actually compare different radioactive sources to see which one has a higher level of radioactivity. Thank you for watching.